Now, I will continue the example. Take the function y equal to f of x, say mod x, in the interval -1, 1. We will discuss the existence of Rolle's theorem for this particular function. As you observe that in the graph, mod x function is continuous in -1, 1. Second condition is going to be mod x is differentiable, the existence of the derivative in -1, 1. As we observe that mod x function is equal to plus x and minus x when x is greater than 0 value, f of x is equal to plus x, when x is negative, f of x is minus x. So, in this case, the derivative of the function is, you will get as h tends to 0 positive side and h tends to 0 negative side, will get different values for derivative of the function. Therefore, the function is not differentiable in -1, 1, even though f of -1 is equal to f of 1 here. Out of 3 conditions of Rolle's theorem, 2 conditions are satisfied, but the derivative is not exist. Hence, the Rolle's theorem does not holds good. Another example, you take the example, say f of x is equal to x square. We will verify f dash of c exists or not. So, the interval it is taken a comma b is equal to -1, 1. First condition, x square function is continuous function in -1, 1. Second condition, x square function is differentiable, derivative exists in open interval -1, 1. The third condition of Rolle's theorem, f of -1, that is -1 square, it is equal to 1, and f of 1 is equal to 1 square, which is 1. That means f of -1 equal to f of 1 equal to 1. All the 3 conditions are satisfied. Hence, Rolle's theorem exists. Therefore, in between, for a given function f of x is equal to x square, there exists a value c belongs to -1, 1. That means f dash of c is equal to 2c, and which is equal to 0 as per the Rolle's theorem. 2c is equal to 0 implies c is equal to 0, and that belongs to -1, 1. Therefore, Rolle's theorem holds good. So, these are different examples to understand the Rolle's theorem. Now, we will discuss the mean value theorem, which was first proved by French mathematician Joseph Louis Lagrange. Therefore, this is also called Lagrange's mean value theorem. The statement of Lagrange's mean value theorem as follows: let f of x be a function which satisfies the following 3 conditions. First one, f of x is continuous in the closed interval a b. Second condition, f of x is differentiable on the open interval a b. Then there is a number c belongs to a comma b, such that f dash of c is equal to f of b minus f of a divided by b minus a, or equivalently f of b minus f of a is equal to f dash of c minus b minus into b minus a. Before proving this theorem, we will discuss geometrically also. See, in the figure 3 and 4, I have taken 2 points a and b. These two functions are within that interval a comma b. F of x is differentiable. That means you have drawn the tangent at that particular point. You are observing in both the figures p. In the first figure you observed that. In the second figure p1 and p2 you have observed that. Therefore, you have drawn at these particular points tangent here. Therefore, the value exists. Now, slope of the secant or the tangent line AB in this case is equal to f of b minus f of a divided by b minus a. Since f dash of c is the slope of the tangent at the point C f of c, by the mean value theorem, it says that here there exists at least one point C on the graph where the slope of the tangent line is same as slope of the secant line AB. In other words, there is a point P where the tangent line is parallel to the secant line AB. Hence, geometrically, now we have proved the Lagrange's mean value theorem. Now, theoretically, we will try to understand the existence of Lagrange's mean value theorem. Thank you. We will continue in the next session.